Swayam Prabha. Digital India. Educated India.
So, before I start the 2D flows, the two things which I want to mention regarding dimensionless analysis, okay, which I possibly did not do. So, you take the problem of this pulsatile flow, and we had this parameter r squared by nu omega multiplying du by dt equals sin t plus 1 by r d by dr of r du by dr. Okay. This is the equation which we got for pulsatile flow when t characteristic is taken as 1 by omega. This is what you would get, and the argument we made was that for low r squared omega by nu, we set the LHS to 0, the left hand side, because this is a very small quantity. There is an implicit assumption which I mentioned it couple of times, but I thought I will make it more clear today, that when you make your equations dimensionless, one of the things we have to ensure is that these terms which I am putting in the circle, okay, these terms are all of the same order of magnitude. Usually they will be of order 1. Okay. So, when we make equations dimensionless, the terms are of the same order of magnitude, order 1. I am talking about the in this case du by dt. In dimensionless case, 1 by r d by dr of r du by dr, these are all of order 1. Only then, if they are of the same order of magnitude, I can neglect this term for small r square omega only if they are of the same order of magnitude. For example, when I say small, this r square omega by nu, supposing it is 10 power minus 5, but if this derivative is 10 power plus 5, then this will be of order 1, which is the same as this order. Okay. So, you have to keep in mind that there is a basic underlying assumption, or we have to ensure when we make things dimensionless, that these terms are of the same order of magnitude 1. Only then I can say this is a small term, I can neglect this term if this is small. If they are of different orders, if this is of order 10 power 5 and that is of order 1 and this is 10 power minus 5, then this becomes order 1, that becomes order 1, I cannot neglect it. Okay. So, keep that in mind. So, when you do this problem, okay, any problem. The other thing which I want to mention is, when you make equations dimensionless, there are more than one dimensionless parameter which can arise. Okay. So, we can have more than one dimensionless parameter describing a system. Then normally what we like to do is we like to talk in terms of what is the effect of changing one of the dimensionless parameters, changing Reynolds number or changing Strouhal number. Okay. What we do is, when you are changing one of the dimensionless numbers, we are tacitly assuming that all the other dimensionless numbers are constant. Okay. When you are analyzing a problem, you will be studying the effect of one parameter at a time. You will not be varying 5 parameters and trying to study the effect. I mean, you can do it, but you won't understand what is happening. So, you do one parameter at a time. So supposing the experimental parameter which is within your control in this problem is the frequency with which you are giving the input, and you want to study the effect of frequency. So, frequency right now is occurring in my Strouhal number. You have to ensure that the frequency does not occur in any of the other numbers, in any of the other dimensionless numbers, because only then changing frequency affecting only Strouhal number. So, when you make your analysis for changing Strouhal number, experimentally how you will change the Strouhal number is by changing the frequency. Okay. But it should not affect some other numbers, because when plotting a graph, you will plot for the Strouhal number, you are assuming your Reynolds number is constant, or you are saying something else is constant. If that changes because of changing frequency, then that graph does not make any sense. Okay. You are weighing 2 parameters at a time. So, point I am trying to make is, some of the parameters can be controlled experimentally, and if you are interested in studying the effect of that parameter, you make your dimensionless numbers in such a way that that particular parameter occurs only in one dimensionless number, not in 3 dimensionless numbers. Okay. So, experimentally we vary a parameter and find its effect. Okay. For example, omega in this problem can be varied, suppose. Okay. So, we must ensure this omega occurs only in one dimensionless parameter. In our problem, there was only one dimensionless parameter, the Strouhal number, so there was no problem. But there could be some other problem where there will be 3 dimensionless parameters, and omega should not occur in the other 2. That is what I am saying. Okay. So, when you are varying one parameter, you are varying only one dimensionless parameter, then it makes sense for you to talk about it. Okay. So, it should not appear in other dimensionless parameters. Okay. This way we can study the effect of one parameter at a time. Okay. So, I mean, there are just a couple of things which I thought you should keep in mind, because if you say you are studying the effect of Strouhal number, and experimentally how do you do it? I mean, this is just not a mathematical exercise. I have 4 dimensional parameters, I fix 4 and then I am varying 1. Mathematically, yeah, but experimentally, if you want to make sense, because you are representing a physical problem. Okay. So, is it really possible to change only Strouhal number? Yes, if omega, because your R is going to be fixed, okay, the radius of the pipe, your new kinematic viscosity is fixed, the only thing which you can vary experimentally is omega, Okay. So, you got to think of it like an engineer from a practical point of view, not just as a mathematical exercise. I am changing a parameter. So, when you change omega, you are changing Stowell number, you have to ensure it does not occur in any other parameters, the other parameters are constant. So, you may have to do some juggling around. Okay. So, these are things which you keep in mind. 2D flows, a classical problem is what is called the lid driven cavity. Okay. So, there is this cavity here, this contains liquid, and this top wall is moving at u equals u naught, this is x and this is y. So, this is a rectangular cavity, okay. These are solid walls, these are all solid walls, okay. These are all solid walls, and to keep life simple, I am assuming as usual z direction goes to infinity, okay. Only 2-dimensional flow. This guy is moving, when this top wall is moving, and these are all stationary, the top wall is moving, it is going to drag the liquid adjacent to it along with it, okay. And so, this liquid is going to go up, it is going to meet this wall, it will come down, and you will have some kind of a vortex like this. This guy will move, it will move the next channel. So, basically what you have is a vortex, a circulation kind of thing inside the cavity. So, this is one way to get 2D flow, okay. This is a very classical problem, and so clearly there are two velocity components, u and v are two velocity components, and we need to figure out the pressure in the cavity. So, I have three unknowns, the pressure field, okay. It is not hydrostatic anymore because there is motion, there is going to be some pressure developed, I need to figure out how the pressure changes, and I need to figure out what the velocity components are. So, the three unknowns which we are trying to solve for, okay. And so, u, v, p are the three unknowns, and so I need three equations. The three equations are going to be your equation of continuity, which is du by dt or du by dx plus dv by dy equals 0, assuming the liquid is incompressible, and then we have rho du by dt equals minus dp by dx plus mu del square u plus rho gx, okay. And then this is the y momentum equation, dv by dt equals minus dp by dy plus mu del square v plus rho gy. All I have done is written the Navier-Stokes equation, okay, and I have just written the left hand side as a material derivative, this partial derivative u with respect to time plus u dot del u, okay. So, x continuity, x momentum, y momentum. So, now the question is, I mean which equation are you going to use for solving which variable? So, there are two velocity components and there are two equations of motion, the x momentum and the y momentum. So, clearly if you want to look at it in a very simple manner, things have to be symmetric. I will use the two momentum equations to find the two velocity components, okay. So, basically the the other option is use one momentum equation for velocity and the other continuity for the other velocity, that is the other possibility. But I mean, if you are going to use a momentum equation for one of the velocities, you should naturally use the other one physically speaking, okay, to make sure you don't have convergence issues and all that. So, normally what is done is the momentum equation is used for the velocities and continuity is used for the pressure, okay. And there is a small problem in the sense the continuity equation does not have pressure in it, correct. So, how can you solve for pressure when the pressure does not arise in the continuity equation? So, when you are directly solving for the flow field using u, v and p, directly getting the velocity components, these are called the primitive variables, okay. This is called the primitive variable approach, okay. And the way you would actually do it is you would assume some kind of a pressure field, you will solve these equations for the velocity, okay, that is the algorithm, because it has to be done numerically, there are nonlinear terms sitting here, okay. And then you will get a velocity field, you will then substitute this velocity field in your continuity equation, see if your continuity equation is satisfied. If the continuity equation is satisfied, then whatever you had assumed pressure field is correct. If the continuity equation is not satisfied, you will use this error to correct the pressure field, okay, and then again impose it in the momentum equations and then come back, find the velocity, then see if the continuity is satisfied. If it is not satisfied, again repeat the process, okay. So, that is the algorithm which is used, and so the approach is assume pressure as a function of x and y, find u and v from the momentum equation, check if continuity is satisfied, if not modify the pressure and iterate. So, again there is a very classical algorithm which does this, okay, and this algorithm is actually called simple, but it is not simple, okay, it is semi implicit something. So, I mean this is just an acronym, the simple algorithm is just an acronym for solving this kind of a problem in primitive variables, okay. So, basically this is the classical approach. I mean if you are interested in of course at the end of the day you will have to write code, you will have to do numerical simulations. So, this is the classical algorithm for finding 2D flow fields in primitive variables. So, now the question is I do not want to do this kind of an iteration, I want to see if I can avoid this kind of a iterative algorithm where I have to solve for V and assume pressure, get u, v, then get this thing. So, is there any other way to do it? And yes, the answer is yes, and we use what is called the stream function vorticity approach, okay, for solving this, and I just introduced stream function in the last class, I am going to do it again. So, to avoid this kind of a thing, an alternative method is to use the stream function vorticity formulation, okay, and that is what we are going to discuss. First of all, what is a stream function vorticity, and then we can derive the equations. The idea is what you do in this approach is you do some manipulation and eliminate the pressure which is occurring in the Navier-Stokes equation. Okay, I will just write that. So, here we eliminate the pressure from the Navier-Stokes equation. Okay. And so, you know, you do not have this problem of having to use the continuity and then doing this iterative process. Okay. So, before I tell you how you eliminate the pressure, it's actually quite simple. Supposing you have to eliminate the pressure, what would you do from these two equations? You could differentiate this equation with respect to y, you will get the mixed derivative. You can differentiate this with respect to x, you will get a mixed derivative, and then you subtract and you can eliminate, right. We are going to do that eventually, but just to tell you what we are going to do. Okay. So, that is what I mean by saying we eliminate the pressure. So, pressure is gone, I have two equations and I can hopefully solve. So, anyway, so let us consider a 2D flow like we did, and let us say this is my velocity, this is actual velocity that I have at a particular point. This has two components now, this has a Vx component and this has a Vy component. At each point velocity can be arbitrary, it has both x and y components exist, because that is what I am saying is a 2D flow. Okay. There are two velocity components now, and at any point if you have the velocity vector, I can resolve it in x direction and the y direction. This is your vector addition rule. Okay. So, basically what I am trying to tell you is that this is theta, this is a slope. So, what is tan theta? That is going to be given by Vy by Vx, the slope of the curve. Now, supposing I have, if we imagine a curve in space such that the velocity vector is tangential to the curve at every point. Okay. Just imagine a curve, at every point the velocity at that point is tangential to that curve. Okay. So, then we can define a function which is constant on that curve. Okay. So, basically I have this is the curve, at this point the velocity is tangential, I am drawing a tangent to the curve and the velocity is tangential at every point. Okay, the velocity of the liquid is actually tangential to this point. So, this curve is called a streamline, and the function which is constant is called the stream function, okay, and it is denoted by psi. So, this is this Greek letter, the way you pronounce it is like this. Okay. So, the point is, this is my streamline, this what I have drawn is a curve, and at every point on that curve the velocity at that point is tangential. Okay. So, if I have a curve like this, I am saying I can define a function psi which is a constant. So, psi equals constant on the curve, which means d psi is 0. There is no change of psi, and this implies the partial with respect to x dx plus d psi by dy equals 0. Okay, which means dy by dx equals minus d psi by dx divided by d psi by dy. Okay, and I am saying that the slope at every point is going to be coinciding with the velocity vector. So, the slope of this must be the same as the slope of this velocity vector. So, this must be equal to Vy by Vx. Okay, so dy by dx, this is the slope of the curve. This is the slope of the velocity vector, because they are basically tangential, they are parallel to each other. The slope of the curve and the slope of the velocity vector have to be the same. Okay, and this is what I get. So, basically what I am trying to tell you is, so I am going to, my job is to find psi, right. I told you the great function called stream function, we need to find out what psi is, what is the relationship between the psi and the velocity vector. I am going to use this. So, Vy is defined as minus d psi by dx, and Vx is defined as d psi by dy. Okay. So, this streamline is basically a function, a curve. Every point, tangent and the velocity are basically parallel to each other. The velocity vector and the tangent are parallel to each other, and I use that to get this relationship. So, what we want to do is, and what I did last time was basically took an example and I told you how to find the stream function. Let us do that again. So, we are going to assume, consider a case where Vx is equal to x. This is just to illustrate the idea. Okay, you can have some other velocity field and you can just follow the same procedure, but just to help you think about how this works. So, this is just for the sake of illustration, and I know how to integrate up to x. X square is difficult for me, so I will just keep it at x. Okay. So, now what is Vx is x. So, d psi by dx is Vx, which is x, the velocity component in x direction, that is x, and psi will be, when I integrate this I get, yeah, something is wrong, psi is xy plus, because this is a partial derivative with respect to y, when I am integrating it I am going to get a function of x. Okay, I get a function of x. This is my, it is not an arbitrary constant anymore. This arbitrary constant now is a function of x. Why? Because this is a partial derivative with respect to y. So, when I differentiate this, derivative of f of x will be 0. When I differentiate with respect to y, I get x. Okay. So, this is because of the, if this total derivative, it will be constant. Partial derivative function of x. Great. Now, I want to do the same thing using this definition. Vy is equal to minus d psi dx. Okay, but before I proceed, I want to calculate, if given Vx is equal to x, what will Vy be? Vy has to satisfy the continuity equation. Okay, so from continuity, Vy has to be minus y. Only then continuity will be satisfied. Derivative of Vy with respect to y plus derivative of Vx with respect to x will be 0. Okay. And so, now we have substitute this back inside here. So, now minus d psi by dx is equal to minus y. Okay, is equal to Vy, which is minus y. So, again I integrate this, psi will be xy plus now some function of y. I am integrating with respect to x. So, when I integrate this I get a function of y. Okay. Now I compare this stream function with this stream function, same flow field, right. So the stream function has to be the same. When I compare this, I get xy plus some function of x and xy plus some function of y. The only way I can have these two equal is if the function of x and the function of y are both equal to a constant. Okay. So this implies that g of y is equal to f of x equals constant. Let us say, yeah, let us say c. So I am saying psi is equal to x y plus c. The point is, if you were to draw this, I mean draw these curves on which, so the streamlines are the curves on which psi is constant. So you will get x y equal to constant. Okay. So these are basically your hyperbolas, rectangular hyperbolas. These are x y equal to constant. So this particular flow field is going to be of this kind. Vx is positive, Vy is negative. The velocities are going to be like this. This is what we saw last time. The now what about this constant? This constant c is taken as 0 because as a reference condition. Let me explain to you what I mean by that. See, what we are interested in is the velocity. Okay. The velocity does not depend upon the actual magnitude of psi. What it depends upon is the derivatives. So the changes in psi only are important. Okay. So only the changes in the stream function are important. So you can choose this to be any constant, because there will be some value of psi here, there will be some value of psi here, both will get changed by the same constant. So when you look at the derivative, you will get the same value. The velocity is going to be determined uniquely. Okay. So supposing you take this constant as 0, maybe this corresponds to psi equal to 1, this corresponds to psi equals 5, suppose. This is 1 and 5 if I am assuming c is 0, but supposing I take, instead of 0 I take 5, or let us take 10, then this becomes 10, this will become 15. Okay. You will just get shifted by 10. So the difference is the same, and what you are interested in is the derivative. So the actual value of the stream function does not really matter. The differences in the stream function is the one which tells you what the velocity field is. Okay. So this could also be 10, it could also be 15. So you take the derivative, you will get the same thing, d psi by dx, d psi by dy will be the same. Okay. So that is the reason it does not really matter what this constant is. If you want to take 10, you can take 10. If you want to take a million, you can take a million. But we just want to deal with 1 0, we just move on in life. Okay. So because, so the stream function is going to be defined within an arbitrary constant. You are free to choose whatever constant it is. So when you solve problems, you will take, the stream function at one point as 0. That is your reference value. All other stream functions are going to be defined with respect to that reference value. Okay. So reference value best to take is 0. If you want to take something else, you take something else. So we will do what everybody else in the world is doing. We will take this reference as 0, put c equal to 0. Okay. So is this clear? Why the c is 0? Because it is only differences which matter. You take on this curve, if you choose the c so that it is 1, this will become 5. If you choose the c so that it is 10, it becomes 14. The difference has to be the same. This has to be 14. No? 1 and 5, difference is 4. So 10 and 14. So keep that in mind. The actual magnitude of what the stream function is on a particular curve is not very important, because it can be changed by an arbitrary constant. It is a constant on the curve, you can change it to something else. Okay, let us move. So that is the flow field for this particular thing, Vx is equal to x and Vy equal to minus y. What I want to do is, to do is see, write the equation of continuity in terms of psi. So, I have du by dx plus dv by dy equals 0. That is my continuity equation. Okay? And u is, what I say, u was d psi by dy. So, I am going to write d by dx of d psi by dy, correct? I mean, I erased it, it is d psi by dy plus d by dy of, what is v? Minus d psi by dx. What do you get here? The mixed derivative minus the mixed derivative. So, these cancel. Okay, I get 0 equals 0. The point is, the stream function always satisfies the equation of continuity. Okay, the stream function will always going to satisfy your equation of continuity. So, mass balance is the way we have defined the stream function is the continuity equation is satisfied. So, you do not have an additional equation to satisfy, because the way I define my stream function, continuity is satisfied. And to understand it better, psi always satisfies continuity. Okay, and to understand this, take, I mean, I am going to take the same problem, okay, and this is a streamline. What I have drawn is two streamlines, okay. On that curve, psi is constant, psi is some other constant on the other curve, and this is x and this is y. So, this is psi. So, let us call this psi A and this is psi B. Psi A is the constant value, psi equal to psi A on this curve, psi equal to psi B on the second curve. Okay, and let us say, oh, I should not call it A and B. Let us say the CD, and I am drawing this EF. So, A is, this is the point B, this is the point A. So, on the stream function, on the streamline passing through A, the constant value of psi is psi A. So, psi is equal to psi A here. This is the constant, okay, and psi equals psi B, the another constant on the curve going through psi B, on the curve going through B. So, psi is the function, psi B is the constant value, psi A is the constant value. Now, I want to look at this line CD, okay. At C, what is the value of psi? It is psi A. At D, what is the value of psi? It is psi B, because it is on the same curve, okay. So, now what do we have? D psi by dy into dy plus d psi by dx into dx equals dx. Okay, you know what is happening? I think my psi and my x's are looking the same. This is not good. You have to make it better. Okay, I will take care. So, this is d psi, this is the definition. Along CD, y is constant, y is not changing. So, dy has to be 0. So, along CD, dy is 0, there is no change in the y, only x is changing. So, what do I have? Along dy is 0, so I have d psi by dx, dx is equal to d psi, and d psi by dx is nothing but, what did we have? D psi by dx is minus Vy, right? Yeah. So, minus Vy dx is equal to d psi, and I am integrating this from C to D. So, this minus By dx is going to, what does it represent? This is the velocity in the y direction integrated over x. That is going to give me the flow rate per unit length, per unit depth, because velocity is only one dimension, velocity to area is flow rate. Okay. So, this basically tells me this is the flow rate. So, and what is integral d psi? It is the psi at C minus psi at D. Okay. So, basically what I am saying is the delta psi represents the flow rate per unit depth. Okay. You can look at the same thing over this line EF. Over EF, x is constant, y is changing. Okay. So, over EF, I have d psi, again I am writing the same thing, dy over EF, x is constant. So, this does not contribute. Okay. And what I have is d psi by dy is Vx dy is equal to d psi, integrated as y goes from E to F, psi will go from psi E to psi F. So, psi E minus psi F equals integral Vx dy from E to F, and this again is the flow rate through this. Okay. Again the flow rate. What I am trying to tell you is this difference psi E minus psi F is the same as psi A minus psi B. This difference is also psi A minus psi B. Okay. This d psi is also psi C minus psi D, but on this is curve is psi A, it is psi B. So, the psi value is the same. So, the flow rate here is the same as the flow rate here. It makes sense because the velocity vector is only tangential. So, there cannot be any flow perpendicular to the streamline. Okay. So, basically any fluid which is flowing between this gap, between these two streamlines, is always going to be within those two streamlines. Okay. So, that is the one of the reasons why your conservation of mass is automatically satisfied. Okay. So, I am just trying to make you look at it physically. So, point is the difference in the stream function between two streamlines gives you an idea of what is the flow rate between those two streamlines for a 2D flow rate per unit depth. Okay. So, to conclude, what I am saying is this is psi E minus psi F, and this is also this d psi, I will just write this as minus psi C minus psi D. Okay. So, the difference in the psi values is the flow rate between the two streamlines. Hence, the conservation of mass is satisfied automatically. Okay. And since velocity vector is tangential, fluid cannot penetrate the streamline. Okay. So, basically on the streamline there is no perpendicular component of velocity. So, this is on the streamline the normal component of velocity is 0, okay, because the velocity is tangential, that is how we defined it, no normal component. But there is a tangent, but it is not behaving like a wall. If it behaves like a wall, what does it mean? The tangential component will also be 0. So, this is tangential component is not 0, okay. So, a tangential component is not 0, hence it only partially behaves like a rigid wall. So, yeah, hence you can say the slip is there along the streamline. Slip is there means the no slip condition is not satisfied, okay. No slip means velocity is 0. No slip is not satisfied. So, what I have to do, basically now I have gotten your stream function and you know some of the properties of the stream function. So, tomorrow what we do is we know how the velocity is related to the stream function, v y is minus d psi dx, vx is d psi dy. You go to the momentum equation, substitute everything in terms of stream function, eliminate pressure like I described, and you will get one equation for stream function, and that you can solve for, okay. That is your basically your stream function vorticity approach. You solve for stream function using some numerical method, and once you get the stream function you can back calculate the velocity field and the pressure field, okay. That is the standard approach used for stream function vorticity, and you know that is advantageous. We will be doing 2 or 3 problems in the class looking at applications where stream function vorticity is used. Thank you.